Look at problem 7. The question provides us with a chain of equations and hints us to do the proof by induction. Before we look into the question, let's do a quick review about induction. So induction, maybe you know, it's sort of like the domino effect. We prove that the first tile can actually push the second tiles down, and then we prove somewhere for the nth pile can flip the n+1 tile over. Then we can prove that every pile in this series can be flipped over, which means that the statement we want to prove is working for every tiles, because if the nth tile can push the n+1 tile, the second tile can push the 2+1, the third tile, and the third tile can push the fourth tile, and it will go on and on without ever stopping. So let me provide some steps for doing induction. First thing, we do prove it works for statement 0. The second step is you assume as n works. The third step is show that the next statement as n+1 works as well. Then you prove it works for every integer for this statement. For this question, we have to get a brief idea of what xn is. This is the first thing we should do. Guess an expression in terms of n for xn. We don't randomly guess it. We should find some pattern. So we have to do some experiments before writing the expression. So let's try to find out what x1, x2, and x3 is. This is very essential. So for x1, obviously it is 2/3. So we have 2/3 plus 2/x2 equals 3. This gives us x2 equal 9/3 minus 2/3, which is 7/3. So x2 is 6/7. So 6/7 plus 2/x3 equals 3. So x3 equal 14/15. So have you ever noticed some pattern? First of all, it is obvious that the denominator is 1 greater than the numerator. And the 3, 7, 15, it shows another pattern that they are the power of 2 minus 1. So 3 equal 2 squared minus 1. 7 equal 2 squared, 2 cubed minus 1. And 15 equal 2 to the power of 4 minus 1. So yeah, now we can guess an expression for xn, which should be 2 to the power, for the denominator it is 2 to the power of n+1 minus 1, and the numerator should be 1 less, so it will be 2 to the power of n+1 minus 2. Fair enough. So we have done the first step. Prove it works for S0, because S1 equal 2 to the power of 2 minus 1, 2 to the power of 2 minus 1 minus 2 would be 2/3. And now we have to assume Sn works. So assume Sn works gives us xn equal 2 to the power of n+1 minus 1, 2 to the n+1 minus 2. So we we just assume it is correct. Assume this is correct. And the third step is we want to show that xn plus 1 also works the pattern we assume. But let's look at what we have. We have the chain. We have this the chain equation. So right now what we only have is xm plus 2 over xm plus 1 equals 3, right? This is currently what we have. So let's express xm plus 1 with xn. So it will be xm plus 1 equal 3 minus xn. So xm plus 1 equal 2 over 3 minus xn. And we substitute what we get into it. Be 2 over 3 minus 2m plus 1. 2. Okay, let's proceed. Just some calculations. Plus 1 minus 3 2 flip over minus 1 times 2 times 1 plus 1. For the denominator, this stage, because we can see that it is basically just the power of 2, so we try to make let 3 be 2 plus 1. Okay, let's keep going, but with one more page, so we can keep writing, I guess. The numerator should be 2 to the 2 minus 2. And actually, this numerator is what we want, but we have to make the denominator what we want. So it will be 2 to the 1 plus 2m plus. Yes. We cancel out these things. And then we get yes. And this is actually what we want for xm plus 1. So we also show that xm plus 1 works as well. And we just use the assumption that xn works to deduct that xm plus 1 works. Xm plus 1 also fit the guess that we come up with. So yeah, we finish our proof by induction for problem 7. That's the end of my solution to problem 7.